Hello and welcome back, Forum. Today we're doing something kind of unique. We're actually going to be combining our knowledge of definite integrals with our knowledge of Golang to implement a very simple solution to the definite integral problem. And if you don't remember everything about integrals, don't worry, I'm going to do a quick recap, but you should definitely check out more videos about integrals that I'll share in the description down below. Let's dive right in. So let's first start off with a simple function like f of x, where we know whatever x is something along this line, and y is of course this way. And if f of x is equal to, let's say, x, well, that means that for every time, if we were to make a table here, we were to say we have x and then we have f of x, right? And we're taking an x, so if x is 1, well then what would be the answer to our function? It'd also just be 1. So our y, which is the f of x result, sometimes we just write y is equal to f of x. And that's because a lot of times we're just saying that y is the result of this function. So in this function where let's denote like this is number 1, this is number 2, and this is number 3, if for every single time we're having an x, like 1, we need to actually go to 1 on the y-axis along with the x-axis. So as long as we're traveling along this way, we're going to mark things along this way that are the result of our function. So really quickly, I'm just going to change the color of my pen to green and put our first mark as this one right here, 1, 1, right? Because x is 1 and the result of our function, which gives us y, we can just call this y, is also 1. So now when we get to 2 and 3, when we get to 2, again, 2 is 2. We're just saying that x is equal to the result of the function. So there's nothing to do. And we have 3, so now we have this. Now when you're dealing with functions like this, what if I told you that I wanted you to calculate the area under these 3 dots right here? So just to give you an outline, what if I said to give me the result of basically whatever function it is that gives you the result of this triangle here, right? So all the area here, what if you had to calculate that? Well, you would probably say something like, from geometry, I remember that half base times height will give us the result of the area of this triangle. So if we know that our base, which is 3, and we know that our height, which is just the same as the y, how high we are on the y-axis, is also 3, well, you would simply say that 3 times 3 is 9, and then that 1/2, right? We multiply 1/2 by 9, and we get 4.5, which would actually give us the answer, right? So the area right here of this triangle is 4.5. Not too shabby, right? So what if instead I told you that we had the function f of x is equal to x squared? Let's make our x and our y table. And what's f of x when x is 1? Well, f of x y is going to be 1 because 1 squared is 1. 2 is going to be 4, and 3 is going to be 9. And if I was to start plotting this along this graph, 1, 1, which is right here, would go right here. That's our first point. 2, 4 would go right here. That's our next point. 3, 9 would go all the way up here. That's the 9th one. And if I start drawing a line from here to there, like so, and I kind of go in through all these things. Just let me retry that. So I go through all these things, I end up with this curved line. And if I just draw a line here coming down to the 3, if I told you to find the area under this triangle, it's not as simple as the half base times height anymore. We could start placing rectangles underneath it. So if we put like a rectangle here, and we put another rectangle here, and we put another rectangle here, and another rectangle here, well, we have 1, 2, 3, 4 rectangles. And if we were to figure out the length, right? This is the length, and this is the width. If we were to figure out the length and width of this rectangle, and the length and width of this one, and this one, and this one, we would get kind of close to our answer, but we wouldn't really get the answer because we have all this area right here, 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 all the area right here that we're gonna miss out on, right? So we'll call this red stuff like our error margin, right? Like we're actually gonna be wrong. Our answer is gonna be off by however much red we have. And one way to reduce the red is by making the width smaller, and there, if we make the width smaller of our rectangles, we'll be able to fit in more rectangles. Okay, so the less width we have, the more number, the more number of rectangles. Okay. So now we're going to make smaller rectangles, right? So we're going to decrease the width. So we're going to say that this is our first rectangle right here. Boom. We're going to make this the next rectangle right here like that. Boom. And then this is the next one, and this is the next one, this is the next one. And look, we've already kind of, we're getting close, right? So if we were to like connect all these to all their components here, just take me a second. What you'd notice is that now that we've decreased the width and increased the number of rectangles, we have a more accurate answer, right? Because now the error margin that we had earlier is so much less. Look, it's just this little bit. So although whatever our answer is going to be is not going to be 100% right, we're getting pretty close. So let's formalize what we've done here so far. We've taken the integral, which is the area under a curve, from 0 to 3. So if I was to write that, I'd write 0 and then I write 3. Now that means the integral from 0 to 3 of what function? The function x squared. Okay, so we've come up with a cool approximation idea. Now how can we implement that in code? Let's do it now. Alright, so if we were to write a function that takes in this stuff, first of all we need to pass in the interval limits, so a and b, whatever we want to call them. It's in our case going to be 0 and 3 when we pass it in, right? And then the other thing is that we have a dx, we're going to call this thing, right? So that's our dx, meaning our smallest width. And we can adjust that width because based on how big or small that width is, we're going to be able to fit more and more rectangles. So if we give it a big width, like we'd only might be able, if we give a really big width to a really fat, rectangle right here, we have a lot of error margin right here. So we're gonna, again, we want to stick with the smallest we can when it comes to the dx as we adjust it. And then we have to label our dx. The dx will be an integer, but it's actually going to be a special type of integer. It's going to be a float because we're not just going to go by ones. We're not just going to say dx here is 1. If dx here is 1, then that means literally it's this rectangle and this rectangle. And again, you can see the amount of error margin. So we're going to make dx a float. It's going to be a number between 0 and 1. So it could be any decimal point. So 0.01, 0.001, whatever. Floats are basically the data type for decimals. Now I'm going to add this thing called result here, which is going to hold our answer, and I'm going to initialize it at 0.0. So now we have to write a for loop, and this is the real main part here. Let's call f of x equal to x to the power of 2, right? That's what our f of x is, right? I'm just writing it out. Well, if we were to define a for loop here, what we'd have to say is that for a all the way to b, right? Because this is our a right here, and this is our b right here, the 0 and the 3. For a all the way to b, what do I want to do? I want to add to the result variable f of x times dx, because f of x is whatever is this y-axis. This is f of x. This is the result of our function, and dx is the width of each of these rectangles. So if we want to know the width, if we set the width of the rectangle to be big, then we're going to have these big fat rectangles, right? Meaning that our answer will be more inaccurate. And we want to basically say that we want to increment by dx. So let's write this in code form here, and it's going to make a little bit more sense, right? So here I have an empty file called integral.go, and I'm going to run it here at the bottom. The first thing I'm going to do is I'm going to declare package main. I'm going to create my main function. I'm going to mention some of the imports I need. I need the fmt import, which lets us do stuff with strings, and I need the math import, which is going to help us write our f of x. So first we have our starting and ending interval, a and b. Then we have our dx, which is the width of the rectangle. Then I'm going to declare a as 0 and b as 3. So from 0 to 3, and our dx as 1. Now if I have our function declared right here, f of x is a function that just says return x squared. Math.pow, so the power of x squared. Now I'm going to say that the result is going to start off as 0, and we're going to start integrating. So from A all the way to B, we're going to keep integrating by adding f of x times dx to our result and stepping by the amount of dx that we have, which is the amount of rectangles, and then I'm just printing out the result. So now let's go ahead and run our code. If I run the code here, you'll see that the definite integral within the interval 0 and 3 is 5. Now the actual answer is 9 based on the rules of calculus. So why are we getting 5? Well, the actual reason why we're getting 5 is because our rectangles are still so fat. We want more skinny rectangles. So let's make our dx smaller. Let's make that change in x 0.5, let's say. And now if I run this code, you can see that we're getting closer to the answer, 6.875, right? 6.875 is close, but let's make it a little bit skinnier. Let's go to 0.25. So now they're only a quarter as big, right? And if we run that, now we're getting closer to the answer, 7.9. Okay, let's make it so that 0.000001. Okay, so now we have this tiny thing. We have tiny skinny rectangles. Let's see what the answer is. And now the answer is 8.99995. So we're getting really close. We're never actually going to hit 9 technically, but this is as close as we're going to get. And as you can see, we just wrote this nice looking code as an elegant solution to an approximate. We're finding the definite integral from 0 to 3, where the function would be x squared. And so there you have it, finding a definite integral using Golang. I hope this video has been helpful for you, and if it has been, don't forget to like and subscribe, and I'll see you guys in the next one.